Hello everyone, welcome back. This is video number 4. Today we're going to be talking about stoichiometry. So before we do, I want you to look back at page 149 and make sure you've done your Cornell revisions, questions, and summaries on that page before you start this video. So when you're ready, look at page 153, have out your calculator and your periodic table. And there was some question yesterday about what notes you should write down. I think pretty much everything on this document should be written down on page 153 of your notes. So today's essential question is, how can an unknown quantity of a substance be determined using a balanced chemical reaction? And this gets to the heart of this concept of stoichiometry. So let us, for one moment, write the definition of reaction stoichiometry. Reaction stoichiometry involves the mass relationship between reactants and products in a chemical reaction. The thing is, it requires a balanced chemical reaction because once the coefficients of a balanced chemical reaction are balanced, that tells you something about the ratio of each substance. So a balanced reaction tells you the mole ratio, which is a conversion factor that relates the amount of really any substance in a reaction to the other substances. It says that how many of each type of reactant will yield how many of each type of product. So I'm going to give you an example, but the last thing that I want you to write down before that is that a mole ratio comes directly from those coefficients in front of a substance in the balanced equation. All right, so let's get this example down here. For the equation, 2 wheels plus 1 frame reacts to form 1 bike, we're going to write all the possible mole ratios. So there's a couple of them. We can see that there's going to be 2 wheels that need to react for every 1 bike produced. But there's also going to be a frame, a ratio of 1 frame for every 1 bike produced. And I can't forget that there are 2 wheels required for every 1 frame. So all of these mole ratios are a possibility. So if I write them all out, I can write them either way. 2 wheels for every 1 bike, or I could write it the other way. 1 bike for every 2 wheels. Those things mean the same thing. But don't forget that the number 2, for example, must stay with wheels in order for it to be a true statement. So all of these are possible mole ratios that I could use to perform stoichiometry on this reaction. So let's try another example, but this time let's use an actual chemical reaction. Try this one. Write all possible mole ratios for the following reaction. 2 mercury oxide reacts to form 2 mercury and 2 oxygen gas. So just like we did for this example, I want you to write down 2 of this mercury oxide per every 2 mercury. You're also going to need to relate this quantity mercury oxide to oxygen, and then the third ratio should be oxygen related back to this mercury. So see if you can write all of those out on your own. So I got these 3 ratios. 2 moles of mercury oxide for every 2 moles of mercury. 2 moles of mercury oxide are necessary to produce 1 mole of oxygen gas. And finally, 2 moles of mercury are produced in conjunction with 1 mole of oxygen gas. All of these statements are true, and I can use any of these conversion ratios depending on what units I need and what units I need to cancel. The stoichiometry of a balanced chemical equation, it allows us to solve really any type of problem where you have a known quantity of a substance and an unknown quantity of substance. That's what stoichiometry is, going from some known quantity using a balanced chemical reaction to come up with some expected value of a different substance. All right, so now let's do a problem using this bike example. How many bikes can be built using 24 wheels? Now, this is pretty easy to do off the top of your head. You could probably just very quickly say 12 bikes because it's going to take 2 wheels for every 24 2 wheels for every bike. You have 24 wheels. That's one that we can do very easily. But when we start getting into the chemistry of it, using molar masses, using numbers that are not whole numbers, and using more complex ratios, we're going to have to continue using our picket fence method. So let's set up what it is that we're given and what it is that we're trying to find. I see that this problem says that I'm given 24 wheels. That's the first thing I'm going to write down. I also need to take into account this mole ratio, that there's going to be 2 wheels for every 1 bike formed. And finally, what am I trying to find? How many bikes? Some number of bikes. Once I write it out, it looks like this. 24 wheels, I have a mole ratio of 2 wheels for every 1 bike, and I'm trying to find a number of bikes. So you can see this is going to be a picket fence with 2 links in it. The given 24 wheels is the first thing that we should put into our picket fence. Now, without knowing anything else, I know that I will need wheels on the bottom here in order to cancel out this wheel value. So I look for the ratio here that gives me some information that relates what I have, wheels, to what I want, bikes. So the 2 wheels goes on the bottom, the 1 bikes goes on top. Now I can cancel out my units of wheels. I'm left in units of bikes, which is what I want here. So now I can do the math on it. And just like we predicted, we should get 12 bikes. 24 times 1 divided by 2 is 12. All right, so let's try an example using some actual chemistry. In this example, we're going to convert from moles of substance A, and it could be any substance, to moles of some other substance B. So in this example, it says, how many moles of LiOH are needed to react with 20 moles of CO2? 20 moles of CO2 is what I'm given. I can see that there's an implied coefficient of 1 on CO2, and the other value that I care about is moles of LiOH. So I look for the other substance, LiOH, in the equation here. That's what I'm trying to find. So these 2 species over here on the product side are relevant to make this a balanced chemical reaction, but they're not anything that I really care about in terms of how this problem is being asked. So these are the 2 things I'm actually going to be comparing. So I need to write a mole ratio for those. Let's set up our given and find. So I'm given 20 moles of CO2. I'm trying to find moles of LiOH. So I just pull the coefficient of 1 mole of CO2 for every 2 moles of LiOH. And I'm going to use that mole ratio to set up my picket fence. So as you can see, I'm only going to need 2 pickets in this fence. I've got a given here and a ratio. So let's write 2 pickets. All right, what I have, the 20 moles CO2, always goes in the beginning. I see that I have moles of CO2 on top. I want that to cancel, so I'm going to choose this value, this moles of CO2, to go on the bottom here. The ratio that that corresponds with is that there's 2 moles of LiOH required, so I plug that in. All right, let's see if these units cancel. I started with moles of carbon dioxide, CO2, so I'm going to cancel that. I divide by the fact that there's 1 mole of carbon dioxide in this chemical reaction that react with 2 moles of lithium hydroxide, LiOH. And so that's what I'm left with. I'm left with 2 moles of LiOH, or I'm sorry, left with moles of LiOH as my unit. That's what I was trying to find. So at this point I can go ahead and punch this into my calculator. Oops. When I do that, I do 20 times 2 divided by 1, and I'm sure you can all do this in your head, but I come up with 40 moles of lithium oxide. So I used what I knew about a certain number of moles of carbon dioxide to discover how many moles of lithium hydroxide I would expect So this is what stoichiometry is. You go from something that you know to something that you don't know much about. All right, let's try another example. So this time we're going to convert from moles of a substance, A, to grams. This is what's different. We just did a mole to mole conversion. Now we're going to do a mole to gram conversion of a completely different substance, substance B. So what is it that we're given? What mass of CO2 is needed to react 3 moles of H2O? 3 is the only number I'm given, so that must be my starting point, my given. I'm also going to go ahead and highlight that reactant in my equation so I can reference it. And what I'm being asked to find is mass of CO2. Now remember, whenever you see that you're being asked for mass, you need to remember that we're talking about grams here. So I'm also going to highlight this mass, the CO2, in my chemical equation. This 6 mole of CO2 ratio to 1 mole of every water ratio is going to be what I need to pull out. So go ahead and set up your given and find. Let's see if you get what I get. All right, here's what I'm given from the problem, 3 moles of water. I see that there will be 6 moles of carbon dioxide needed to react with 1 mole of water in order to form whatever these products are here. The other piece of information I need is the molar mass, because I'm going to be converting into some final grams of carbon dioxide. So I've gone ahead and added up 1 carbon plus 2 oxygen, and I got 44.01 grams of carbon dioxide. And remember, 1 mole per whole, so 1 mole of carbon dioxide. So you can see now that I have 3 steps, a given and 2 ratios. This means I'm going to need a 3-picket fence. So let's draw that in. 3 pickets in my fence. Always, always, always start with what you're given in the very first column. If I have moles of water, I need to cancel moles of water. So I'm going to skim and try to find another spot where moles of water repeats itself. Moles of water, moles of water, moles of water. Ah, there it is. 1 mole of water. That's what I'm going to put on the bottom. The 6 moles of carbon dioxide will go on the top. And now I'm in moles of carbon dioxide, so I'm getting closer to mass of carbon dioxide, but I'm still not in units of grams like I want. So I'm going to look for something that will allow me to cancel moles of carbon dioxide. Ah, here it is, molar mass, 44.1 grams of carbon dioxide for every 1 mole of carbon dioxide. 1 mole goes on the bottom, grams go on the top. Before we do the math, let's make sure our units cancel. Moles of water cancel, moles of water cancel. Moles of CO2 on top, moles of CO2 on bottom. I'm left in grams of CO2. Is that what I want? Yes. Now I can punch it in my calculator. 3 times 6 divided by 1 times 44.01 divided by 1. Let's see what we get. $792.18 grams of CO2. Hopefully that's what you came up with as well. All right, one more example, and then we'll call it a day. How do we now convert? We've practiced converting from moles of A to moles of B. We've practiced converting from moles of A to grams of B. Now can we convert from grams of A to grams of B? This is a little bit longer. It's only going to be one extra step. So here's the problem. How many grams of NH4NO3 are required to produce 33 grams of N2O2? So let's identify this as what we're given. We're only given this one number. And grams of this amount is what it is I'm trying to find. So let's set up our given and find. We'll first need the balanced chemical equation. I see that I'm given 33 grams of N2O in the word problem, I see that I'm asked to find some number of grams of this other species in the word problem. And now I need to think about how do I get from grams of N2O2 to moles of that same thing. So this is where I'm going to use the molar mass. I add up 2 nitrogens and 1 oxygen. The molar mass of this first substance should be 44.02 grams of N2O for every 1 mole of N2O. So that's going to take me from grams to moles, and now I can use a molar ratio. So I see that it's going to take 1 mole of this substance undergoes a reaction to produce 1 mole, as implied by the 1 coefficient there, of this substance. So this is a 1-to-1 molar ratio. I need to write that down, even though the dividing and multiplying by 1 won't change my number. I have to treat the units. So I see there's 1 mole of N2 produced by 1 mole of NH4NO3 here. 1 from this coefficient, 1 from this coefficient. And the final piece of information I need to get from grams of this, or from moles of this substance to grams of this substance, is the molar mass of this compound. So when you add up 2 N's, 4 H's, and 3 O's, I came up with a molar mass of 80.06 grams per mole. Don't forget 1 mole per whole. So I just took an N, I added 4 H's, another N, and 3 oxygen. So I can see this is going to be a 4-step picket fence. I have 1/2, 3 ratios. Let's put in a picket fence that has 4 steps. Here we go. Once again, like always, I need to start with what I have, grams of N2O2. I know that I will want this unit to cancel, so I'm going to find another unit of grams of N2O in my list. Okay, I used that. Oh, here it is, grams of N2O. So that's the number I put on the bottom, the number in unit. It corresponds to the fact that that's the mass of a mole of this substance. So that's what I put on top. Now I'm in units of moles of N2O. I need to find another ratio that contains N2O. Here it is. Here's 1 mole of N2O for every 1 mole of this NH4NO3. So this unit, this number, 1 mole N2O, goes on the bottom. This other species will go on the top. And I'm nearly done. Finally, I'm going to use this last ratio, this molar mass of this NH4NO3 compound. I put the fact that in 1 mole of this compound, it has a mass of 80.06 grams. And now I double check my units to make sure I can go ahead and do the math on it. So let's cancel out grams N2O2 and grams of N2O2, moles of N2O, moles of N2O, and then I see on the top I have moles of NH4NO3, and finally moles of NH4NO3. Let's make sure our final unit, grams, is what we want. Oh, look at it, it matches. So we know we set it up correctly, and now it's just a matter of multiplying through. 33 times 1 times 1 times 80.06, divide by 44.02, divide by 1, divide by 1. I punch this into my calculator, and I come up with 60 grams, 60.02 grams. In other words, it requires 60.02 grams of this compound to get 33 grams of what I want. So this is a very useful technique for chemists, because if I'm trying to make, a certain amount of anything, I need to know how much to start with. If you're trying to make 12 cookies, you need to know how much of each ingredient to start with. And that's basically what stoichiometry is. Okay, that's all we're going to do on this page for today. Hopefully you got all of that down. Please make sure you pause these video notes and when you need to, so that you can get all of that information. Make sure you bring your calculator Monday. I will be doing a materials check. It cannot be a phone. It has to be a calculator you're going to use on the test day. And we will practice with this a lot. So I hope you all have a wonderful weekend. Take care.